AFM. And so since one of the set of instruments we have is AFM upstairs, I thought it would be nice to have a few words about AFM. And after the presentations, anybody that wants to go to the optical spectroscopy lab or see the AFM instruments and talk to us, we'd be happy to follow up with you.
Thank you, Israel. Thank you for the invitation. So for the next hour and a half, we'll be talking about no. Okay, so for the next 20 minutes, we'll be talking about FM spectroscopy. It's sort of this old new thing, right? Where it's been around since the 80s. And in some places, it really picked up. In some places, it didn't. Now, I consider myself a person that is good at many things, but not great at anything. Right? So I think I excel a bit at XPS and data processing, understanding XPS. But I've done many things, and FM is one of them. So I'm going to be sort of trying to present you FM as it is. And then you can decide. And we have a couple of instruments on the campus that may or may not be useful for your research. Okay. So, I'll go briefly of the concepts of bulk and the surface, because they are very important, obviously, for this meeting. Talk about scanning probe techniques, so that's very different from what we talked about up till now. Then I'll focus on atomic force microscopy, so a bit on the fundamentals, on the how things work, what are the most important parts, imaging modes, very important, and then what we can do beyond simple imaging. There is force spectroscopy, and then the fancy stuff, as Israel said. So, for example, tip enhanced Raman spectroscopy. I think it's very relevant to this talk. So, let me tell you what you probably know already, right? So, what is bulk versus surface? So, bulk composition is really composition of the total volume, as well as morphology. So, bulk morphology is really this particle size based for distribution thing. So it's really three-dimensional. Now when you start talking about surface, it's a completely different thing, right? So here the surface chemical composition is trickier to identify. You use instruments such as XPS or LISE. And on the surface, that's where things happen. Right? So all the physical properties of the surface are very, very important for any reactive. Right? So we disregard the bulk effectively because it's already it's diffusion limited. So I always ask people to think about it as adsorption versus absorption. Right? Adsorption is on the surface, whereas absorption is invisible. So if you think about any material, be it catalyst, bio, effectively all of their activity stems from the surface interface. So that's where my interests are. And moving on, that's where I'm going to be spending the rest of my talk, on the surface of the samples. And turns out that a very good technique to probe surfaces is scanning probe technique. And the terminology here is that they all are scanning probe techniques. So if you see atomic force microscopy, conductive atomic force microscopy, scanning transmission, and so on, Kelvin probe, magnetic force, electrostatic force, all of them are scanning probe microscopies. Now the trick here is that AFM is kind of this very rugged, simple technique, is there a lot for non-conductive materials. So people started doing STM scanning tunneling. But then you have to have material that is conductive. So AFM was developed for non-conductive material. Now AFM and all the rest of the techniques, they utilize probe interaction with the surface. That's all there is. And they measure certain response, certain observable, if you will. It can be a force between the tip and the sample. It can be potential difference. It can be magnetic fields, and so on and so on. Now the beauty of that is that probe techniques are not diffraction limited. So what Israel showed you, limitations, right? Spot size, it's because light-based techniques are diffraction limited. Well, in here we use some probe which is not light. So we circumvent diffraction limitation. Another good thing about it is that it's z-axis limited. What I mean by that is that if you take your optical microscope or scanning electron microscope or any other microscope, you measure things in 2 dimensions, right? You infer particle size, you say it's 300 nanometers in diameter. If you have fancy TM instrument, you can do something like tomography, right? And reconstruct 3-dimensional image, because you don't have a good field real of the 3rd dimension in those techniques. In FM, it's directly quantifiable. Very, very important. Imaging in liquids. So AFM is not limited to ultra-high vacuum. It can work in the ultra-high vacuum. It doesn't have to. It can work in liquid. And then it can, probe many physical properties of the sample. It doesn't have to do imaging, right? Once you have tip there, you can poke at things, right? So you can do many other physical sample properties. It's adhesion, hardness, elasticity, what have you. Again, AFM can be operated under UHP, but doesn't have to. Right? So bunch of response signals generate essentially an image for you, right? But this is AFM, so this is probably Ford's image. This is conductive AFM, so this is already a conductive response. STM, that's again conductive response, right? Because this is tunneling based. Electrostatic force, so this is diamond coated with some impurity, so this is just the electrostatic potential. Diamond indentation, we can poke those samples very hard. And magnetic field, things like that, they exhibit magnetic field, so magnetic force microscopy can map that out. Very diverse field of applications. Now, how does that work? The principle is rather simple, really ingenious when you think about it. All you have to do is very sharp tip right there. You use some scanner. It can be Z and XY decoupled, or they can be together. And all you need to do is to put a laser beam on it and position that beam onto photodiode. So whenever this cantilever is deflected, that gets registered in photodiode and fed into your controller. Now, if we specify one thing to remain constant, it can be deflection, it can be force. As a set point right there, that set point will adjust your Z feedback to maintain the parameter constant. So you can imagine if you want to maintain force constant, right, between the sample and tip, you scan, and then tip approaches something that really changes your force dramatically. That gets reflected in photodiode, fed into controller. Set point says we need to maintain that parameter. So it lifts your Z-axis up, right? And scans further. And by mapping that out, you get your topography. So at the heart of it is the piezoelectric scanner, obviously. What else? The beauty of that is that in material science, we've known for a while that if certain materials can move in the presence of external electric field. Simply put, if you apply potential, things will start moving. Now, what potential? So typically, you have to apply a fairly large potential. So if you have 1 centimeter ferroelectric material, if you want it to move by 1 micron, you have to go to 380 volts. So it's those things are sizable. So you have physical motion, and that obviously right there is related to the non-linearity problems, right? So you get non-linearity, hysteresis, creeps, and other things, right? Nowadays they use these closed loop scanners to partially eliminate them. Nevertheless, AFM is not your direct imaging technique. In the microscope, what you see is what you get, right? In optical microscope. In AFM, you have this tip that really, is connected to all the electronics. So it's not direct imaging technique. So now scanners, all sorts of scanners by now. So the ones I'm used to are these single hollow tube scanners where it has 4 poles, and you apply potential, and that makes that scanner move, right? So this is probably what's called the DIC or DI design, early design. Later, people decoupled the XY scanners, so this is what Asylum uses, so you can scan in XY and have a third scanner independently, right? So that helps with all the linearity problems. What determines resolution in AFM? Several things. And it's not straightforward, but it's kind of simple. First of all, you have to have very, very sharp tip. So to your first approximation, the sharpness of your tip will determine your resolution. And tip radii, typically, it's about 10 nanometers. You don't really know what it is, right? You need to stick it under the microscope with the apex. They approach 3 nanometers. They have fancy things now glued to those, such as carbon nanotubes and so on. So they mess with the resolution. But so it's approaching nanometer or so. It's not the only thing that matters. It's a scanning technique. It's a scanning technique, right? So typically people scan, let's say, 512 lines, and every line has 512 points. So if you scan 1 micron, 512 points, your resolution is 1 micron by 512 points, right? So your resolution is 2 nanometers. If you scan 512 microns, and you use 512 points, what is your resolution? 1 micron, right? So again, I need to remind you that it's not true atomic imaging technique. Why is that? Idealistically, you would think that your tip is atomically ideal, right? There is 1 atom sitting in there. It's not. It never is. So people, image and publish routinely, graphite, like structure with that. When you think about it, if you have a tip, it's not only the first atom that will have sufficient interaction with the sample. It's number 2, number 3, and the rest of the atoms, they're going to see those surface atoms, right? So if only that first atom saw your sample, this missing atom, there clearly would be a void in it. Unfortunately, number 2 atom sees that. Number 2 atom sees that. And number 3 atom sees that. So eventually you get some sort of averaged thing, right? That looks like that. So it's not true atomic imaging. And that is associated with many image apathy. So if you have dull probe, that will cause broadening. If you have double tip, you will see 2 things repeated, right, instead of 1 pattern. I can operate this. The tip width will determine the whole size, so it's not going to be square necessarily. And damaged tip will change your pattern. So now, when you image, there are several ways to image it, but you can be on classical curve of attractive and repulsive regime, right? So if in a repulsion, you are very, very close to the sample. It's called contact mode. In the attractive regime, you are far away, it's called non-contact mode. So contact mode is tricky. So if you scan, for example, some protein in liquid buffer in contact and non-contact mode, you see that once you drag your tip, you eventually damage your sample. Right? When it's in non-contact mode, it's much easier to work. So people tend to work in non-contact mode, not general rule, and essentially you just tap that thing, right? So of the free amplitude. So if you come closer, your amplitude drops. If you're far away, it's very high. So that's how you know how close you are. Right? Now, mind you, if you have liquid droplet in there, Non-contact mode will show it to you, right? Because it will go above. Contact mode might not see it and go through, right? So again, you have to understand what you're doing there. Because your imaging sort of concept will determine your result. What is it good for? So I thought Israel would like this slide. It's good for if you push it stronger, you can image defect size. So this is non-reconstructed, non-reduced series sample, and this reduced series sample. So in the reduced series sample, you get oxygen vacancies, and then you can see your triangular, linear, and so on. Yours truly did a lot of work in there, but I tried to go to sort of high relative humidity, which is very difficult. So I monitor change of cleaved calcite sample at high relative humidity as a function of time. And then get some ion mobility, calculate some movement values. Another thing beyond topography we can get is amplitude and phase. And it's kind of difficult to do. You have to do the math. Oh, computer does the math. But you have to multiply your response voltage, right, in the detector by the drive voltage, and you get certain parameters which is called amplitude and phase. And what that does is, if you have two different domains of the same size, AFM won't pick it up. It will see it as flat, right? So topography will not show that, but phase will. And this is exactly true. P3 and P4 regions are of the same height in topography, but in phase image, clearly very different composition. You can probe that later on with some fancier things such as near optical field microscopy. You don't have to stick to the imaging. You can do force microscopy in there. Since you can shake that thing at very high amplitudes, you can just simply controllably pull it up and down, right? So what you do is you sit far, far away, approach it, ram into the sample, your deflection starts increasing. If you start detaching from the sample, the tip gets caught because of your adhesion, and then it releases and goes back. So with that, you can do phase imaging, right? You can see that the sample is very different phase. And you can measure the adhesion properties of those two different areas and get some adhesive sort of response. A very neat thing is that you can modify that tip with something that is sample specific. So it's going to bind specifically to certain places in the sample. And you can do that at the atomic scale, right? So this is silica with some metals on top. So if you modify that tip, it's not that easy as it looks. With something that is sample specific, right, it will map that out for you. And from there you can simply get every atom, whether it's silica, so that's the strongest covalent bond, right, or some other interactions. Very neat thing. You can probe hardness. If you push it into the sample, you'll probably indent it, and from there you can get hardness, which is just force over area, or you have a small jet.
Jonas?
Yes? So, Israel, I'm going to ask you, so what AFM can do for you? It's difficult, right? Because one thing AFM is just imaging, very good resolution imaging. But Israel has a huge lab that is built on optical microscopy, which is resolution limited. Can we combine those two things? In my last slide, I'm going to show that yes, we can. Can we resolve spatially with AFM and get spectroscopy information of FTR? So Berghuis in Utrecht did that. He used what's called TARS, right? Tip enhanced RAM. So the field around the tip is so enhanced that most of the signal comes from the tip. And the tip now, we know the size. 10 nanometers, what have you. So that's the beauty of it. So he probed with two lasers. One laser does not do anything to the sample, it's too weak. The other one induces reaction. So he starts probing with 633, nothing happens. You have one peak in there, you do it on 2. And then he shines 532 for a while and starts probing again. You can see that other peaks appear, which are due to NN blocks. So this is how you get essentially almost, well, not single molecule, but very spatially resolved spectroscopic information using that FM technique. Is that good technique? Probably it is, but limited to seconds integration time. You have to use surface active metals, and so on and so on. So nothing is perfect. So with that being said, FM is imaging technique. It's one of those scan and probe techniques. You can provide z-axis information, various environments, and can be combined if you are patient enough, right? With things such as SNOM and TERS to get spatially resolved chemical information. So I want to thank symposium organizers in Israel for giving me a chance to talk about something I've done a few years ago. Thank you.
First, I want to apologize to all of you. There is a time mix-up, and there's a class coming in for an exam right now. So that's why we're ending kind of abruptly. We do have time.